Hi, everyone. Today I will present our NeurIPS paper on online continual learning. And this is some work I did with Rahaf, Lucas, Eugene, myself, Min, Laurent, and Tina. So in continual learning, we're currently focused on solving the catastrophic forgetting problem, which is that when a model learns a new task, it completely forgets how to perform the previous task it learned. So there's a couple of ways to alleviate the catastrophic forgetting problem. But one popular family of methods is rehearsal. So simply put, when you train on a new task, you're going to rehearse the previous ones. Um, there's two popular ways to achieve this. Um, the simplest one is when you sequentially train on task, you're going to save some data from the previous task, and you're going to retrain on those data points later on. We're going to call this experience replay or memory replay. Another way to achieve rehearsal is instead of storing old data as is, we're going to compress it with a generative model. So you're going to train a generative model continually, and when you want to rehearse on past tasks, you're just going to generate some data and train on those generated data points. Now, one important point I omitted is that you're going to randomly rehearse on the previous task. This sort of assumes that when you're learning a new task, it's causing a equal amount of interference on the previous task you've learned. But this might be a bad assumption. For example, if I'm learning a new language, maybe this would cause more interference on my language skills than on my ability to ride my bike. So in this paper, we ask, can we do better than random rehearsal? So I will explain the method with a little cartoon, and then we're going to dive deeper into it. So let's say you've trained a classifier to recognize the digit from 0 to 4, and now you would like it to recognize the digit 5 as well. So on the left, you have the current loss landscape for this new task in parameter space. And on the right, you have the loss landscape, but in input space or in task space. This might not be super clear right now, but it's going to get clearer in a second. So the first thing we're going to do is we're going to take a data point from the current task, and we're going to take a virtual update step. This will most likely decrease the loss for the current task, but will also most likely increase the loss on the previous task. Next, we're going to find where that loss would increase the most. In this case, it's on the digit number 3 because the 3 looks a little bit like a 5. And next, we're going to augment our mini batch with the digit number 3 here. And now we're going to take a real gradient update step. And hopefully this will not increase as much the loss on digit number 3. Okay, so we can apply our method to experience replay or generative replay. It's a little bit easier to explain with experience replay, so I will start with this one. So you're training a classifier continually. You have a standard objective function. You're going to store memories in a buffer. And when a new data point comes in, you're going to take a virtual update step. And then you're going to look inside the buffer for the top values where the interference is maximized. And here the interference is the difference between the loss of the virtual model and the current model. So just to summarize, you look inside your buffer for samples that you're forgetting the most, basically. And then you augment the mini batch with those samples. And hopefully you don't forget as much. Okay, so now I will explain our method applied to generative replay. So now instead of storing old data in a buffer, we're storing it in a generative model, which is composed of an encoder and a decoder. Again, a new data point comes in. We're going to take our virtual update step. And now, instead of looking inside the buffer for those samples where interference is maximized, we're going to look inside the latent space of the generator. And we're going to do this by gradient descent on the latent codes to maximize interference on a generated samples. So long story short, we're looking inside the latent space of the generator for a sample that we're forgetting the most given that virtual update. And we also have a little constraint to encourage diversity in the retrieved samples. Okay, so we're now going to look into qualitative results for the split MNIST dataset. In this dataset, we split MNIST into 5 tasks. First, we have some offline experiment results, so more than 1 epoch per task. So now you can see that when the model is learning the last task, which consists of binary classification between 8s and 9s, when the model is learning the digit 8, it's fetching sometimes the digit 3, which is similar to an 8. And when it's learning about 9s, it's fetching the digit number 4. So everything seems to be working as we anticipated. In the online setting, it's much harder. So as you can see, the VAE baseline is generating fading digits or that are not always recognizable. But in our case, again, when we're learning about the digit 8 and 9, we're fetching again the number 4 and the number 3, which seems to be recognizable. So qualitatively speaking, it seems that our method can outperform the baseline. I'm now going to quickly talk about the quantitative results. So first, on the split MNIST dataset and the permuted MNIST dataset, both our methods can outperform their respective baseline, both in terms of accuracy and in terms of forgetting. And we can also achieve the best performance over all the baselines. And for the split CIFAR 10 dataset, we only applied our experience replay method because generative replay doesn't work yet on harder datasets like CIFAR. And again, here we can outperform the baselines. So other stuff you can find in the paper is another approach, which is an hybrid between the experience replay and the generative replay approach. We have results on Mini ImageNet, which is a really hard data set for continual learning. We have an ablation study. We have results on online continual generative modeling. And we also have a nice code base that can reproduce all of the results. So thanks for listening.